Okay, so far we discussed about how to design spur. So there are two criteria to design the spur. One is strength criteria, other one is wear criteria. Of course, you need to check for both. So then, if the wear is strength and wear are within the acceptable limits, then you can say the design of spur gear is fine or safe. So now we'll move on to the helical gears. Here the design of this helical gears is also similar to the spur gears. In fact, what we'll do here is we'll try to convert this helical gear into an equivalent spur gear, because we already know the design procedure of a spur gear. If it is possible to convert this helical gear into an equivalent spur gear, then whatever procedure we adapted in case of spur gears, the same procedure can be used for this helical gears also. So that means only thing is there any way of converting this helical gear into a equivalent spur gear? That we'll call it as formative gear or virtual gear. So here, in fact, we are going to do that. So we'll discuss how we can convert a helical gear into an equivalent spur gear. Then what are the parameters, or what are the, if you know the parameters of the helical gear, how we can convert those parameters into equivalent spur gear parameters. Then apply the design process. What we follow in case of spur gear, we'll apply the same procedure. That means same steps, beam strength, wear strength, all those things are same. Whatever concept we discussed earlier, it is going to be same. So therefore, only thing is we need to find out what is the equivalent parameters of this helical gear parameters in terms of equivalent spur gear. Okay, so that we'll see now. So once it is done, we can directly take up the numerical problems. So for that, okay, so the basic difference between spur and helical gear, like how I said, the concept, in order to arrive at concept, how to convert this helical gears into a spur gear, first we should know what is the difference, then how we can map that difference to equivalent spur gear. So we know that in case of spur gear, the teeth are cut parallel to the axis of the shaft, whereas in case of this helical gear, they are cut in the form of a helix and a pitch cylinder. So that means, say, if I take a spur gear, if this is the spur gear and this is the axis of the shaft, we discussed this, the teeth are cut parallel to this axis, something like this. Whereas, if I take a helical gear, maybe single helix, so the teeth are cut like something like this. They have some inclination. This is called helix angle. So they are cut in the form of a helix. So this is called helical angle. So this is the difference. So now, once you understand the difference, and also we'll see the differences. So in this case of spur gears, the contact between meshing teeth occurs along the entire face width of the tooth, resulting in sudden application of the load, which in turn results in impact conditions and generate noise in high-speed application. So because your teeth are cut in a straight portion or parallel to the axis, whenever one tooth on the pinion come in contact with the tooth on the gear, so there will be, the contact is something like this, that the contact is sudden, as well as it will come in contact with the entire face width of the tooth. So this will result in a impact kind of loads and also generate a lot of noise. Whereas in case of this helical gear, the contact is gradual and also it is progressive. So in case of helical gears, the contact between meshing teeth begins at a point on the leading edge of the tooth and gradually extends to the diagonal lines across the tooth. There is a gradual pickup of the load by the tooth, resulting in smooth engagement and quiet operation even at a high speed. So here if you take two helical gears, this is another one, of course. So here the contact will be first at the leading edge. So it will contact will take place and gradually, because you have a angle something like this, two angles will be like this. So first the contact will be like this and gradually it will move to the diagonal line across the tooth. So only thing is, because of this gradual engagement of the teeth, the load is not suddenly applied, it is gradually applied load, and also because of this gradually applied load, it will be a smooth operation, and that means there is no noise even if you operate this helical gears at very high speeds. Helical gears are used in automobiles, turbines, high-speed applications, even up to 3000 meters per minute. So the speed you can go for maximum 3000 meters per minute, and also the some of the applications of these helical gears are they can be used in automobiles, turbines, and as well as high-speed applications. There are two basic types of helical gears. Again, basic gears, helical gears, there are two types. They are called parallel and crossed. So we'll see what is this parallel helical gear and what is crossed helical gear, and also most of our course will discuss about the only this parallel helical gear. So parallel helical gear is nothing but whose axis is parallel, whose axis is when the shaft axis. So then we can call it as parallel. So anyway, that definition is given here. Parallel helical gears operate on two parallel shafts. So therefore, if the axis of the shafts are parallel, then if you use helical gears to connect those two parallel shafts, we'll call it as a parallel helical gears. So that means I have one gear on this, one gear on this. See, now this is the one shaft axis and this is the other shaft axis. Here I have a gear, one gear, then other gear is something like this. So then we'll call it as a parallel axis, parallel helical gear. Or else if I have shafts axis which are intersecting something like this. The axis is intersecting one upon another, any angle, it need not be 90 degrees. So it may be any angle, something like this also. Of course, it looks like even in 90 degrees if I draw like this and like this. But even other than 90 degrees also, if you use for the axes which are intersecting, we'll call it as a crossed helical gears. Okay, in this case, the magnitude of helix angle is same for the pinion and gear. However, end of helix is opposite. So what is the meaning of this? So when you want to mesh two helical gears, the helix angle should be same. Helix angle, generally we use here psi. Symbol is psi for helix angle. So that means the helix angle for both the gears, that is both for pinion as well as gear, should be same. Then only you can mesh one helical gear with the another helical gear. So this is the first point what you need to remember. That means I cannot have two different helix angles on pinion and gear. So both pinion and gear should have same helix angle, and also the end of helix should be opposite, meaning that, so I already shown that in the figure. Suppose pinion have a right hand helix, then gear should have left hand helix, and vice versa. So that means if for this it is right hand helix something like this, then this one should have a left hand helix like this. So then only the meshing is possible. Or as an opposite, let us say if I take this one as pinion and this one as I have taken it as gear. So if pinion is having right hand, gear should have left hand, or vice versa, means pinion should have a left hand, then gear should have a right hand helix, something like this. So then that is the condition to mesh one helical gear with another helical gear. So the points are two things what you need to consider is magnitude of helix angle should be same. This size should be same for both pinion and gear, and also the end of helix should be opposite. So that means you cannot mesh, even though the helix angle is same for both pinion and gear, same hand of helix gears and pinion cannot be meshed. So the end of helix should be opposite on gear and pinion. So that is the point you need to remember. A right hand pinion meshed with a left hand gear and vice versa. That's what I already said. Crossed helical gears are mounted on the shafts with crossed axes. So when the shaft axes are intersect, then you can, if you want to mount the helical gear on those two axes, then we'll call it as a crossed helical gears. Their teeth may have same or opposite end of helix. So in case of this cross helix angle, depending upon the included angle or how much at what angle they are intersecting, the two shafts are intersecting, based on that either you can go for same type of end of helix or maybe opposite. So just now we say for a parallel case it is opposite hand. So cross in the sense it may be you may have opposite end of helix or you may have same end of helix. Okay, so that is the definition and conditions for meshing of helical gears. So now this is the conventional representation of our helical gear train or gear drive, whatever you can call it as. Here we have a pair of helical gears. So here you can see that this is the convention what we need to follow for left hand and right hand. So if the edge is slanting towards the right, then we call it as a right hand helical gear. If the edge is slanting towards the left, so then we call it as left hand helical gear. So this is a convention you need to follow in case of or while in a pictorial view, if you want to represent, you design the gear, then what type of end of helix you followed for pinion and gear, you need to show it something like this. It is necessary to show the end of helix or the direction of the tooth on the drawing. The end of helix is indicated by drawing the three continuous lines. See, now you can see the notation here. There are three continuous lines. These are the three continuous lines here as well as here. Of course, here it is a meshing tooth. So this is the axis of the shaft and this is the axis of the shaft. The lines are sloping downward to the right side of the piece for right hand helix. For right hand helix, the sloping is towards the right, and for left hand towards the left. That's what we discussed already. The lines are sloping upward to the right side of the piece for left hand helix angle. So both are set. Here I said it is downward, here you can say it is upward. So here it is upward. Then what we will do is, so like I mentioned, we need to find out the equivalent helical gear, equivalents per gear for a helical gear. So therefore, first we should understand what are the terminology what we are using and which parameter is equivalent to its equivalents per gear parameter. So for that, here you can see the picture here. So this is the top view of an helical gear. This is a top view of the helical gear, and then if I take two sections, that is section YY and section XX, auxiliary views, and if I expand that, I'll get section XX is something like this and section YY is like this. Now you can see that here there are from this diagram you can see that there are two pressure angles. This is one pressure angle, we call it as denoted by alpha. In case of spur gear, you have only pressure angle, that is alpha we denoted. But here you have a alpha value and here you have a alpha n also. So alpha n is called the normal pressure angle, alpha is called the tangential pressure angle. And also you can see that here, so this is in the center line of this teeth, and this line is center line of this tooth. So that means A1, B1, A2, B2 are two central lines of the teeth which are adjacent to each other. So now, if I join this from point A1 to this B1, So this B1 and B2 are the same center distance from this point. So from the pitch circle, so they are at same center distance. Now if I join this one, then this A1 B2 made an angle psi with respect to BC. This psi we'll call it as the helix angle. This is the helix angle. And also in the figure you can see that you have a one pitch here, this P, you have another pitch here, Pn. See, as per our definition, so the pitch definition is nothing but you need to consider same point on the two adjacent teeth. You need to consider same point on the two adjacent teeth, and if you measured along the pitch line, we'll call it as a pitch. So, but here, because of this helix angle here also we are considering the same center distance, same point on this teeth as well as on this teeth. This distance between these two teeth we'll call it as a normal pitch. And you have one more pitch here. This is the actual pitch. This is the actual pitch which you measure along the axis. So this is the axis, and this is the center of one point on this teeth, and this point A2 is center of this teeth. So then the distance between A1 and A2 we'll call it as a pitch or axial pitch, what you can say. But here, sorry, it's not axial pitch. You have one more term, that axial pitch is also there. Generally, we call it as pitch. So then you have a axial pitch also, PA is there. We'll discuss that also. Okay. So these are the parameters, and for that we'll try to identify some relation between these pitches with this right angle triangle. So here you have a right angle triangle. This one. So the included angle is psi. So based on that, you can relate Pn to P, or even for P also. Here in this view, you can take it as this pitch is P. So even this one also P. The portion of top view of a parallel helical gears is shown in figure. A1, B1 bar, A2, B2 bar are the central lines of the adjacent teeth taken on the pitch line. So see here A1, B1, A2, B2. So these are the taken on central lines of the pitch line. So this is the pitch line. Then the angle A1, B2, A2. So that is this angle. A1, B2, A2. So this means this included angle is the helix angle and denoted by psi. It is defined as the angle between the axis of the shaft and the central line of tooth taken on the pitch plane. So on the pitch plane, the helix angle is nothing but the axis angle between the axis of the shaft and the central line of the tooth. So this is the central line of the tooth, and this is the axis of the shaft. Because this is a top view. This is top view. The axis is going to be a vertical one, something like a vertical line. So angle between the axis of the shaft and the central line of the tooth taken on pitch line. So we need to take that one on the pitch line. So then, so this is the pitch line. So or else this is the chain. You can take it as pitch line. So therefore, this angle we'll call it as the helix angle and denoted by psi. X-axis is plane of rotation, while y is plane perpendicular to the tooth elements. So here, this y and this x-axis. You consider two sections. So x-axis is in the plane of the rotation, whereas y is perpendicular to the plane to these tooth elements. The distance A1, A2 is called the transverse circular pitch. So this one, A1, A2 will call it as transverse circular pitch, which is measured in plane of rotation. So since your x-axis is plane of rotation, so this transverse pitch is measured along the plane of rotation. So then the distance A1C. So now we taken A1, A2 as P, A1 into C. So that is this point A1 and this is C. This one will take it as the normal pitch. The distance A1C is called the normal circular pitch Pn, which is measured in a plane perpendicular to the tooth element. So it is measured in a plane which is perpendicular to the tooth elements. From triangle A1, A2, C. So that means this triangle. A1, A2, this one, this point is A1, this point is A2, and this point is C. So this triangle A1, A2, C, here it is a 90 degrees, and this is your helix angle. So what you can write it is Pn by P. So is equal to cos phi. So it is straightforward only. So this A1C is Pn, A1, A2 is P. So if I write, this is the right angle triangle. So if I write, this is side, cos psi is nothing but, this is the hypotenuse. This is the hypotenuse. So therefore what you are going to get is, this one opposite adjacent side is A1C, which is nothing but Pn divided by this P, hypotenuse is P, you get cos phi, not phi, psi, it is psi. So then from this you can write your Pn is equal to P. So this is the relation between transverse pitch and normal pitch. So we use normal pitch. We are not going to use transverse pitch P. We will use normal pitch while converting this helical gear into an equivalent spur gear. So therefore we need to remember this formula. So that is, we need to know what is the relation between normal pitch and transverse pitch. Then P into small p into capital P. This is capital P, we'll call it as diametral pitch. So we know that pitch into circular pitch into diametral pitch, the ratio is pi, which is constant. So then if I substitute this one into this, I can write, so that means if I write substitute for small p, here small p is nothing but pi by capital P. If I substitute that here, this is going to be P into P is equal to R. I can say capital P by phi. I think here something is missing. Some phi is missing. Pn can be written as P by cos psi. Then where Pn and P are called normal and transverse diametral pitches respectively. Of course, we are not going to use this term. So, but only thing is this P is nothing but 1 by m. So that you can easily remember. It is 1 by m. So that is okay. I written here P is equal to 1 by m in the above expression. Then Mn. So that is nothing but normal module. So just now we derived the relation between Pn and P. Pn is equal to P cos phi. So then if I know the P, then I can relate P to the module. Similar manner, you can write Mn is equal to M cos phi. Mn is, that is normal module. Then this is the module, or simply we call it as module. Where Mn is the normal module expressed in Mn, M is transverse module. So that means, so now onwards, see in case of spur gear, we design for the module. So now you need to design here, in case of this helical gear, you need to design for the normal module. Once you know the normal module, you can calculate the transverse module also, provided if you know the helix angle. The distance A1, B2 is called axial pitch. So this one, so A1, B2. So this vertical distance, we'll call it as the axial pitch, because this is the axis of the shaft. Along the, if you measure along the axis of the shaft, you can call it as axial pitch. From triangle A1, A2, B2. So A1, A2 and B2. So if you consider this bigger triangle, now here 90 degrees, this angle is psi. PA, if you want to write an expression for this PA, that means nothing but this one. PA, we know this is Pn. Of course, we don't want that one. Here, this is the value. If this triangle includes this, this is P. So now if I take sine phi, or in fact tan phi, tan psi, if I take tan psi, opposite side divided by adjacent side. Opposite side is P, adjacent side is PA. So from this, you can find the relation between PA and P. So PA is equal to P by tan psi. There are two pressure angles, transverse pressure angle alpha and normal pressure angle alpha n. In their respective planes, they are related by the expression cos psi is equal to tan alpha n by tan alpha. Like how these pitches and modules are related, even this alpha n and alpha are also related in similar manner. Cos psi is equal to tan alpha n divided by tan alpha. Then the normal pressure angle is usually 20 degrees. So now we need to take, while designing helical case, we need to consider the normal pressure angle, which is 20 degrees, which is denoted by alpha n. The pitch circle diameter D of the helical gear is given by, so we know pitch circle diameter is nothing but number of teeth into module, or else you can write that one as P by pi. So P by pi is nothing but module only, or capital P is equal to 1 by m. Either way it is okay. So ZP by pi. So E substituted for the capital P, capital P. So then you know that P small p into capital P is equal to pi. If you substitute that to here, or else for phi you can substitute small p into capital P. The small p cancel out, you will get Z by capital P, which is nothing but Z into m. So then here this m we have to consider m. Just now we derive the relation for m and mn. So mn is equal to m cos phi. So if I substitute for this m now, it is going to be Z into mn by cos phi. So therefore this is going to be the pitch circle diameter. Pitch circle diameter of helical gear, not spur gear. We will try to find that equivalent spur gear. What is the pitch circle diameter of equivalent spur gear? Later. The center to center distance between the two helical gears is having teeth Z1, Z2 as the number of teeth is given by. So if you know the number of teeth and if you know the pitch circle diameters, then the average of the pitch circle diameters is going to be the center distance. So dP and dz. If you take dP is the pitch circle diameter of the pinion and dz is the pitch circle diameter of the gear. If you take divided by 2, that is nothing but average, that is going to be the center to center distance between the two helical gears. So that's what we written here. D1 by 2 plus D2 by 2. But if you want to write the same expression in terms of number of teeth and module, so here you need to consider Z1 is the number of teeth on the pinion, then mn by cos phi is the module in the module of pinion. So this should be same. Even for gear also it should be same. If the module remains same, then only you can join or mesh those two gears. So you'll get, this is the expression for the center distance of helical gear. So only thing is here, earlier you have only m here, you can take out that common, but now you have mn by cos phi, because your relation between m and mn is m is equal to mn by cos phi. So in case of spur gear, you have only Z1 plus Z2 into m divided by 2. So that's what you need to take. So but because of this helix angle coming to picture, here you need to take cos psi also into the formula. So like this. So that means, like I said, in case of spur gear, you don't have this one. You need to replace this mn by m only. Now also same equation. Equation remains same, but this m instead of m, we are replacing this m by m cos phi. That is the relation what we derived in the earlier slide. So there is a relation between mn and n. So m is equal to mn cos psi. So this is the relation what we derived. So now in place, this is mn by cos psi. So in this relation, if I replace this m here, I'll get mn by cos psi. That is the only thing. Okay. So that means now we know some relation between the normal values and the pitch values. So once you know that, then the next one more thing what you need to do is you need to find out how many number of teeth, actual number of teeth in a equivalent spur gear. So with that, it is possible for us to convert all the formulas of spur gear as a applicable to the helical gears also. So for that, we need to find out what are the formative number of teeth. Of course, the speed ratio, it is remains same like a spur gear. A speed ratio for helical gears is determined in the same manner as for the spur gear. So I is called the speed ratio, speed of the pinion and speed of the gear. Here, speed is expressed in RPM or radians per second. Doesn't matter. It should be equal to ZG by ZP, number of teeth on gear divided by number of teeth on pinion. So now, like I said, we need to find out what are the equivalent number of teeth of an helical gear in terms of a spur gear. That number we'll call it as a virtual number, because actually you don't have that much number of teeth, but we are finding out what are the equivalent number of teeth on a spur gear. So that's why we call it as a virtual. Actual gear will consist of only, let us say 10, but if I convert that one into equal number of an equivalent spur gear, the number of teeth is going to be some 11 point, some value 11.7 or 11.5 or something like that. So therefore, actual teeth are 11, but they are converted into a virtual number. They are a little bit more. Then what is the formula for that? How I can convert the actual teeth into a virtual number of teeth? So for that, the pitch cylinder of this helical gear is cut by the plane AA, which is normal to the tooth elements as shown in the figure. So here you can consider a section AA. So this is the pitch cylinder. Here, this is the pitch cylinder. So here we cut a section XX. So cut by a plane AA, not XX, it is AA. So this section is AA, and if you expand and if you project this auxiliary view of that one, it looks like something a ellipse. Here the sectional view is going to be something ellipse, which is shown as a dotted line. So for this ellipse, you have a major axis. Generally, you have major axis and minor axis. So here this d by 2 is the minor axis, and then you can see d by 2 cos phi is going to be the major axis. D by 2 is the semi-major, not a complete, semi-minor axis d by 2, and d by 2 cos phi is semi-major axis. So the intersection of plane AA and the pitch cylinder extend produce an ellipse. This ellipse is shown by as a dotted line. The semi-major and semi-minor axis of these ellipses are 2d divided by d by 2 cos psi, this one, and d by 2. Why we want to do this one means we want to find out what is the equivalent. See here, actually your gear is a circular in shape, but if I take a section something like which is parallel to this helix angle here, so its shape is not circular, its shape is going to be something like a ellipse. So I know in case of circular shape, number of teeth and diameter is related something like this, m into z, diameter of the circle, that is nothing but the circle diameter, is equal to m into z, but here it is not a circle, here it is going to be ellipse, which is having a major and minor axis. So on there, diameter, the major and minor axis are given by, semi-major and minor axis are given by these two formulas. So now the radius of curvature R dash at point B is given by. So if you know fundamentals of ellipse, so if A is a major axis and B is the minor axis, you can calculate the radius of curvature at this point P as this R dash. This r dash is given by a square b, but we'll take that what is a and what is b. That is what is a semi major axis and semi minor axis. So if you substitute where a and b are the semi major and semi minor axis respectively, substituting the values of a and b into the expression, your radius of curvature, which is nothing but r dash, is given by d divided by 2 cos square psi. A square is nothing but d by 2 cos psi whole square, and b is d by 2. So therefore 1 d by 2 will cancel out in that, you will get left with d by 2 cos square psi only. So now once you know this one, so then this r dash is nothing but the equivalent Spurgeon radius. So pitch circle radius. So therefore if I multiply this one by 2, I'll get the pitch circle diameter of an equivalent Spurgeon for this helical gear, which is nothing but d into cos square psi. D into cos square psi. So this is going to be the equivalent diameter. So once I know the equivalent diameter, I can calculate equivalent number of teeth or virtual number of teeth also. So that's what I showed in the next slide. In the design of helical case, an imaginary Spurgeon is considered in the plane AA with center at O dash. Here the center is O dash. See how A is mapping this ellipse to the circular one, having pitch circle radius of r dash and module mn. So here now the equivalent Spurgeon of an helical gear is defined as something like this. So that is an imaginary Spurgeon considered in the plane AA. What is the plane AA? The plane AA makes an angle psi with respect to the pitch cylinder. So that is the important thing you need to consider. So then with center at O dash. So center at O dash here, and having a pitch circle radius of r dash. Here you can see, here also you can see. And with module is mn. So therefore the equivalent parameters are the parameters what you are considering for that imaginary Spurgeon is r dash. That means nothing but twice the r dash is nothing but the diameter. And you are considering the normal module, not the module, you are considering the normal module. So it is called a formative or virtual Spurgeon. So therefore this one what I said it is, I said it is an equivalent Spurgeon, but in terminology they are calling it as formative or virtual Spurgeon. Why it is virtual? Because actually it is not a Spurgeon. We are converting that one into an equivalent Spurgeon. So because the actual one is a helical gear, since we are converting that one into some equivalent one, that's why we are calling it as a virtual Spurgeon or formative Spurgeon. The pitch circle diameter d dash of this virtual gear is given by 2 r dash, which is nothing but d divided by cos square psi. Divided by cos square psi. So if I know the pitch circle diameter, I know the relation between number of teeth and pitch circle diameter. So your pitch circle diameter is nothing but module. So here what is the module is considering? The module you need to consider the normal module mn into number of teeth. So here I'll use apostrophe also. For Z I'll use apostrophe. Why? Because these are the number of teeth on this virtual gear, virtual Spurgeon. So therefore I'll use Z dash here. So with this relation, so I know this relation, so I can, if I substitute this, I'll get the Zn. So Zn is nothing but d dash by mn. That is the only thing. If you want to replace the mn by m, then your mn is nothing but m cos psi. So like that also you can substitute. The number of teeth Z dash on this imaginary Spurgeon is called the virtual number of teeth. So the number of teeth on this virtual Spurgeon, we'll call it as virtual number of teeth, and it is given by, see here, your Z dash is nothing but 2 pi Rn by Pn, or else simply you can take it as d dash by mn also. So that's what he has written here. 2 pi will cancel out. So it is nothing but d by 2, this 2 will cancel out. Your d dash is nothing but d by cos square psi divided by mn. So you are going to get d divided by mn cos square psi. So that's it. So here if you substitute d dash is nothing but dy cos square psi. If I substitute that one to here, your z2 dash is nothing but d cos square psi divided by mn. So that's what you are going to get here also. So this is the formula for finding out the virtual number of teeth. We require this because in Spargare, while calculating the Lewis form factor, number of teeth and pressure angle, those are the two parameters we'll choose. So based on the pressure angle and the number of teeth, we'll decide what is the Lewis form factor from the table 28.33. You require pressure angle as well as number of teeth. So here, using this virtual number of teeth, we'll try to find out y value. That is Lewis form factor. This Lewis form factor we'll use in calculating the beam strength, right? So therefore, substituting for D, again is substituted for D. D is nothing but the diameter, the pitch circle diameter of the helical gear. D dash is the pitch circle diameter of the virtual spur gear. So now we have a relation between this D and D dash also. If you substitute that into this, you can say the virtual number of teeth to the actual number of teeth. You will get the relation between virtual number of teeth, which are Z dash, and Z is the actual number of teeth. That is the number of teeth on the helical gear. So that relation is going to be, just now we derived the relation between D and D dash. So here you can see that here. So here this D and D dash, you have a relation. If I multiply this one by 2, so then your relation between D and D dash is nothing but D dash is nothing but dy cos square psi. So now if I substitute that one into this equation, you'll get your virtual number of teeth is nothing but which is related to the actual number of teeth in this way. Z dash is equal to Z divided by cos cube psi, where psi is the helix angle. That you need to remember. And of course, these formulas are no need to remember. These are given in your data book. Just you have to use that one. Before that, you should know what is that concept. That's why I'm explaining all these things. So, right, you have to use to convert the given helical gear into a virtual spur gear. What are the parameters you should know? One is the module you are considering for this virtual spur gear is Mn, and the number of teeth is this one, Z dash is equal to Z by cos cube psi, where Z is the actual number of teeth on the helical gear and Z dash is the virtual number of teeth on the virtual spur gear, and you have to consider the angle as alpha n. We are considering the pressure angle as normal pressure angle, that is alpha n. So with these parameters, if you are able to remember this, so now it is over. So these are the parameters what is required to convert an helical gear into an equivalent or virtual spur gear. So then whatever procedure we adapted for the spur gear design, here also will apply the same, but only thing is instead of m, here we'll use in these equations for helical gear we'll use mn, and instead of alpha we'll use alpha n, instead of z we'll use z dash. That is the only thing what you need to remember. Okay, where z is the actual number of teeth. Okay, so then once you understand that, then so like in spur gear, here also we need to consider, first we need to, while designing this, we need to identify what is the module. So that we are getting here as a normal module, that is Mn. So what are the choices for this Mn? There are standard values, like in case of spur gear also, we have seen on table given in the data book. The same table is applicable for this one also, but only thing is, there we are taking simply m, and here we will take those values as mn. So that is in the table number, if you want, I will tell you the table number also. He has given first choice, second choice, like that table he has given. You can use that one. Yes, it is table number 25.2 in my book. Maybe new edition it is 28.2. Preferred values of a recommended series of modules in mm. Preferred choice 2, choice 3, like that 1, 1.25, 1.5, 2, 2.5, 3, 4, 5, 6, or like that he has given the module values. So we have seen in case of Spurgeon, while calculating it, you are getting a fraction value. How you can convert that one into a rounded value? By choosing a preferred value or second size value or third size value, like that. Here also, the standard, the first preference values for the normal module is 1, 1.25. The same table what he has given in that data book, we'll use the same table to identify what is the first preference, what is the second choice, and what is the third choice values. Whatever he has given, those values will be taken for the normal module. That is what you need to remember. The standard proportions of the addendum and addendum are, the addendum proportion is addendum is equal to 1 normal module and addendum is equal to 1.2 times the normal module, and clearance is equal to 0.25. So you can see that here clearance is, because it's not addendum and addendum. So here when two teeth are meshing with each other, then there is a gap between those two teeth. So between the top of the tooth and the root of the gear. So like this. So here we have a two teeth which are in mesh, something like this. Then here this gap we'll call it as clearance. That clearance can be taken as 0.25 module, normal module. So that is the important point you want to do. So once you know the addendum and dedendum, you can easily calculate the addendum circle diameter as well as dedendum circle diameter. So this is the formula for the addendum circle diameter. Addendum circle diameter is nothing but pitch circle diameter plus 2 times the addendum. So if you substitute for what is D and what is addendum, you are going to get the formula for that. Similarly, you will get the dedendum circle diameter is also pitch circle diameter minus 2 times the dedendum. You will get the dedendum circle diameter. Anyway, these formulas he has given in the data book. No need to remember all these things. Just for the academic purpose, just I am showing you all these things. Then the normal pressure angle alpha n is always 20 degrees. See, in case of this helical case, always the normal pressure angle is 20 degrees. You don't have other type of angle. It is fixed 20 degrees. But the helix angle may vary 15 degrees to 25 degrees. Helix angle can vary from 15 to 20 degrees, but the normal pressure angle is always 20 degrees in case of this helical case. So then after that, we'll see a little bit about this force analysis also. So in case of Spurgeon, we have seen that there are two components of the force, that is radial component as well as tangential component, PD and PR. And we have seen the relation between the PD and PR and P also. Pn is the resultant force which is acting along the pitch line. So pitch line, along the pitch line or resultant will act along the pitch line. But whereas in case of this helical gear, in addition to the tangential and radial component, you have another component, axial component also. That means along the axis also there is a component. You can see it here in the diagram, force diagram. You can see that here. This is the radial component and this is the tangential component, and you have an axial component also there. Because of this helix angle, you have this axial component. So you can see that psi is there. This psi will, this is the resultant force P along the pitch line. So this P is making an angle with respect to two planes here. This, with respect to horizontal plane, this is psi. With respect to this plane, this diagonal, it is going to be alpha n. So you can have axial component of force also in case of this helical gate. So you can see the force triangles here also in the how this tangential and radial. So this is PR is the radial and the PT is the tangential and PA is the axial force. How these forces are related to each other. Of course, this is a PT only here. So this you can see that. So this is the triangle what you get in case of a Spurgeon. You don't have this one. The psi is equal to 0 here. You don't have this triangle in case of this. So you have only your PA is 0. Here in case of this you have a PA also. Then if you want to derive the expressions, of course derivation is not important. Just we'll see what are the expressions for this PD, PR and PA. PT is the tangential component, PR radial component, PA axial or thrust component. The normal pressure angle alpha here is in the plane ABC shaded by the dots. Here you can see that this is the normal pressure angle and psi is the helix angle, which is in the lower plane or plane BCD. You can say, you can take this plane, horizontal plane. So PA is equal to, from this triangle you can write PA is equal to PT tan psi from this triangle, or else it's the same thing. If you here it is in 3 dimensional you have taken, so you write that one as a 2 dimensions, you will get these triangles. PR is equal to PT tan alpha n by cos psi. Then the tangential component is calculated from the relationship. We know this relationship, that is PT is nothing but 2 into or MD divided by D by 2, where D is the pitch circle diameter. Okay, using this PT, you can using this relation, you can calculate PT. Once you know the PT value, you can calculate PR and PA. Straightforward. If you know alpha n, that is normal pressure angle, and if you know helix angle psi. Okay, so I think I'll stop at this point today. Maybe next class we'll go for beam strength as well as wear strength, and also we'll discuss about, or we'll take up some problems. Once we discuss beam strength and wear strength, now we know the concept of how we can convert that gear into an equivalent spur gear. Then we can design as per the procedure of spur gear. Okay, I think if you have, it is clear. Otherwise, if you have any doubt, you can ask it now. So maybe next class we'll take up the problems. If no doubt is there, then you can respond to the attendance sheet and you can leave the class. I am also closing the class. Roll number 3 had already appeared. Okay, only 9 members are there in the class, right?
Exit there, sir.
Okay, no problem.